Uh, our our next speaker for today's second session is Mr. Ajit Patil, sir, a globally accomplished technology and product leader with over 25 years of experience in the data engineering, artificial intelligence, and large-scale digital platforms. Uh, Ajit Patil, sir, had completed his MS, that is data analytics, from Georgia Institute of Technology, US. He currently serves as Senior Director as Visa INC, a global payment technology giant, where he has led strategic initiatives in enterprise data platform, AIML solution, and data commercialization across global market. Patil sir has successfully built and led large cross-functional teams driven multi-million dollar data and AI program and holds multiple patents in areas such as AI, blockchain, and IoT. His rich industry experience and strong focus on innovation make his session highly valuable for understanding real-world application of AI and machine learning. So with this, we are glad, sir, that you are part of this ATAL FDP, and we request to please start with your session.
Thanks, producer. Hi, everyone. Good evening. Fortunately, I remember that it is in my morning time as opposed to my evening time, so that's good. I did read the email earlier today, so I was ready for the session. So that's one good thing. So today, what am I going to do? So today, I'm going to just introduce the basic concepts for AI ML, and maybe I should just go to my agenda slide. Okay, so just a quick introduction on what machine learning is, and most of you should be already aware of what it is, but this is my way of thinking what machine learning is and how I interpret it, right? Then we'll go through some of the ML principles and concepts. And then after that, we'll focus on three machine learning types, obviously supervised, unsupervised, and reinforcement learning. We'll quickly touch upon some of the top ML models which have been used across the industry, and not necessarily just mechanical industry, but across the board. We'll talk about some industry applications of these models. I'll touch upon emerging research, some of the things which were discussed in the earlier session as well, and I'll just touch upon them. And I'll walk through a few case studies, time permitting, and then we'll see how it goes. And hopefully we should have time at the end to talk about what I have shared. Okay, so let me, I'm using my keypad, so it's a little bit tricky for me to move screens. And let me move this down so that, how do I take this out? I don't use Zoom that often, so okay. Can everyone see my full screen? I don't know. I don't think people can speak. But
Yes, sir. Screen is perfectly visible.
okay. So what is machine learning in general? I think this picture represents what it is, right? So in case of traditional programming, what do I have is I have the data and I do write a program which acts upon the data and is executed by a computer, and I get what the output is, right? So what you have is you have the data, you have the program, the computer, and the output. In the machine learning world, we switch it. The way we switch it is we say that this is the data which I am getting it from wherever I'm getting, right? That's my input, right? And this is an output. And then I apply computer where my machine learning algorithms run. And what it generates a program, or it generates what we call as an equation, right? So what you have done is essentially you have changed the paradigm of programming. Okay, so what it means is the machine learning essentially understands patterns, right? It learns patterns from data. Okay? And based on whether I say that whether the outcome is good or bad, or I don't know what the outcome should look like, right? It defines an equation. Right? Now, what I do is the next time I see some data which I need to apply some logic on, I see the data, I see the equation, which is my algorithm, and I get the output. Right? Now, the output could be a prediction, it could be an inference, it could be what does the input actually mean. Right? It's an interpretation of the input. So multiple ways of interpreting data. Okay, so what's the characteristics of an ML model? So we say, okay, oh, here's again, is it a textbook example, right? It says it adapts to new data because data keeps on changing in the real world, right? So accordingly, the model adapts to it. That means it is effectively addressing the changing real world environment and adjusting the outputs accordingly. Okay. The other aspect of it is a non-linear shift. So if I do traditional programming, I say, okay, A plus B is equal to C, right? But that's not true in real world systems. We say A plus B is something close to C. I don't know what it is. So therefore, it captures that non-linear relationship. And A plus B is equal to C is a very, very simple example, right? You could have hundreds of different attributes or input data attributes, which could vary independently of each other and therefore introduce non-linearity in the whole ecosystem. So ML models do capture that non-linearship, which I cannot define with a traditional mathematical equation. Right? So therefore, for a large model, wherein when I say large model, it's a large physical model which understands through its environment large number of attributes, which I cannot represent in a true mathematical model, is somewhere machine learning comes into play. Okay. Any questions? I don't know if I could stop for questions or I could just move along and you could ask questions later. Okay, I don't see it anything in the chat as well, so I'll just push along. Okay, so why now? Like, why machine learning now? Like, machine learning, the field on the research side of the house has been for many, many years. Right. And just an example, I come from Visa. Visa says that, we started using artificial intelligence models somewhere back in 1990s, right, to detect fraud in payment transactions. So, which is what? Almost 35 years. Whereas AIML has started getting speed across the industry in the last 5 years and last 2 years because of the large language models. Okay? But we have always been there. But why does it matter today across the industry, right? A few key data points, right? One is the amount of data, right? So with the advent of IoT, BLE, and so on and so forth, systems generate huge amount of data, right? Now, this data is actually what we need is to capture it, to store it, to persist it, right, and maintain it. Okay. With the cloud platforms or large scale data centers, we could actually do it, right? One of the reasons being that the storage has become cheap. Like, storage doesn't cost me anything. So earlier, this data used to be generated, but nor did we have the sensors to capture the data, nor did we have systems or storage ecosystems to capture, manage, maintain that data. Right? So now everything has come into play. Okay, I see huge amount of data, I could do something with it, right? Next is the advances in computing. Right? As data has gone cheaper, right, we have done something similar, not at the same scale, for compute as well, right? And the introducing of GPUs and TPUs, typically used for large mathematical models, makes things run faster, quicker, right? Makes them run embedded as well. Yeah, because I think people mentioned earlier, what do they call the small scale computers? I'm sorry. Yeah, if someone could have speaking, they could have helped me out. Those embedded computers on the chips and everything, right? So edge computing, right? So what we are saying is, oh, okay, now I have these computing engines which are as close as the data sources, right? And they could run complex algorithms in a much quicker, faster way. Okay, so the overall advances is computing. Oh, I could have done this somewhere back in 2000 as well, right? I could do a neural network and I could train a neural network back in 2000. It's just that it would have run for a year, right? And that it wouldn't have helped me. Now, if I have to do the same thing on today's environments on AWS or GCP, it would run in 5 minutes. So I could do it multiple times and still make it happen and still make it work. Okay, so that's advances in computing. The second big thing as to why ML is now the talk of the day. Right. Next is, oh, wow, why did I skip this? Sorry, my slide is not complete. Anyway, so automation and efficiency, right? So what we see is today in the earlier session we said that okay, here is a process, right? And as the process goes through a multiple number of steps, right? And what I do is I code for those steps in my traditional programming. So okay, if A happens, then I need to B, if else C, and so forth. Okay? But processes are not deterministic; they are probabilistic. So they may change. Things may change, right? So when I try to introduce automation in a probabilistic process using deterministic measures, it would fail. My automation doesn't work as expected. So I need large amount of human intervention. Okay? But using ML, it imitates the probabilistic nature uh, of physical systems, right? Therefore, it can automate a large number of tasks across my process. Okay, so that's the third part of it. Sorry, the fourth part of it, I don't know why my copy paste did not work. I was trying to get it from some other tech. But anyway, the fourth part of it, I don't remember now, and I can't unshare the screen. Maybe I could. Just give me 1 minute. Yeah, okay. The fourth was around competitive advantage. So today we say that if you're not doing AI ML in any process, any industry you're operating in, you are probably going to go out of business, right? So introducing these algorithms within your processes would give you competitive advantage across the board, right? One thing is, and people would have talked about this, especially around large language models, is we have these large language models, and then they are going to essentially get rid of programmers, right? Or computer science professionals in general is what people talk about, right? But the way I see it is these folks spend X amount of time in doing their day and day job, right? Out of that, Y amount of time.
The screen is not visible.
Okay, sorry. Okay, I thought so. Screen. Okay, how do I do this?
Sir,
No. Yeah, I'm just trying to find. Okay, I found it.
okay.
This one. Okay.
Yes, yes. Now is visible.
Okay. So in general, like AIML gives you the competitive advantage, which would help you make that difference, right, in the industry. Okay. So let me go to the next slide. Right. So what does a machine learning pipeline looks at? And then I think this in the few sessions in next few 2 to 3 days, you'll go much more deeper into what a machine learning pipeline looks like and the details of it. Right. So, but let me quickly run through this as well, so that it writes a story, right? And like, what do we start and what the endpoint is? Okay. So it starts with data collection. So here is where we collect large amount of data coming from either from sensors, logs, images, telemetry, what have you, right? And the core of it is the input data which I am collecting, right? And everyone is aware that if I have a bad input to a machine learning model, it's going to learn bad output. So it's as simple as that. So therefore, getting good data is the first and foremost key thing in any machine learning pipeline. Okay, so that's the first part of it. The next is data cleaning. Now, when I capture sensor data, obviously there would be gaps in it, there would be noise in it, right? And so on and so forth. So I need to apply certain aspects of what we call as data engineering principles to clean the data, right? So to make sure that the data is relevant, right? It is clean, it is consistent, and it is useful, and it actually represents the physical process which we are trying to predict for. Okay. Can someone mute? Okay, Vaibhav. Okay. The next step is feature engineering. So today what we say is okay. So so what is feature engineering, right? So let's take an example. So I'm collecting temperature data, right? Oh, I clean data and I have a series of temperature data points for the last 3 months, for example. But a machine learning model would need it in form of a feature, right? And since it's temperature data, I'm looking at, and it's time series data, right? Because it gives me temperature every hour for the last 30 days. Now, to input this data into a model, I need to convert it into something which the model understands. Okay? So one aspect is, oh, I could create a feature which gives me average temperature for the last 30 days, or a daily average temperature for the last 30 days. And that's what I'm going to use instead of using the actual temperature per hour. So that's feature engineering at a very, very high level, right? Then what I have is I have a set of features which I could use to train a model. And then I go into model selection. So there are different models which I could use for different problems which I'm trying to solve. So whether it's convolutional neural network for images, standard regression models, LSTM models, and so on and so forth for time series data. Right. So based on the model I choose is based on what problem I'm trying to solve. Right. So that's the model selection. Right. The next is training, wherein the model learns the patterns from the data. Right. And as in earlier session, we talked about minimizing the error of what the model predicts. Right. And then that's what it does. And that essentially generalizes the model on the data which I'm using for training it. Right. Next step is validation. Now we say, okay, oh, I have this data set, I have trained the model, it works, it predicts what the training data set says, but does it actually work in real life scenarios, which is where the validation data comes in, right? So I now essentially score the model, run the model on this new validation data set, and then I come up with metrics, that's accuracy or root mean square errors or F1 scores and everything, which evaluates whether the model actually performs well in real life scenarios. Okay. After the model, after validation, the model is ready. So now all I need to do is now I need to deploy the model, right? So the model, we say, okay, oh, here is where I integrate this model, whether it's an embedded system or whether it's in the process flow, right? Wherein I need to make sure that this whole thing, starting from feature engineering to validation to monitoring and everything, are embedded in this deployment process, because this deployment actually does the data collection, it does the feature engineering, and it does the validation. So all of these three things should play a big role in here. When I deploy the model, embed the model into a process flow. Okay. The next and the most important thing is monitoring and retraining, or the last thing and the most important thing is models. We say models drift. The models drift because the data drifts, right? And an example would be temperature in general, right? So today, I train a model which helps me predict atmospheric temperature, and it uses the data for the last 100 years, right? It predicts the data. It predicts what the temperature would be tomorrow very well, all good, right? But let's assume that with um, with climate change, the overall baseline of what the mean temperature is globally changes by 2 degrees. Now that the model has never seen. So the next prediction it will do, it will be incorrect because the data, underlying data has drifted. So the model drifts. So monitoring whether the model is actually performing well and retraining it throughout this life cycle as the model continues to be used is the key thing. Okay. I think I should speed up. Okay, so let me move on to my next slide. So what are some of the key concepts around it, right? So earlier we talked about features versus labels. Features essentially are the inputs to a machine learning model. Labels is something which is an output. It's a target state which I am looking to predict, right? Training versus testing is essentially training teaches the model the equation which it needs to generalize, whereas testing actually evaluates that the equation is actually working. Overfitting and underfitting are two key concepts which are rarely understood in the industry. Right? Overfitting is something wherein you have, how would I give an intuition for it? It is if my model predicts everything correctly in my training data sets, and it fails miserably when I actually put it into production, that's called overfitting, because what it is doing, it is following the training data very, very closely. An example saying that, okay, you have captured you have captured data from an engine, right? And I'll try and give as much as possible examples close to mechanical engineering as a field, right? You're capturing temperature data from an engine, right? And let's say it is whatever, it's a 2 HP engine, right? And now what you have done is you capture temperature data, you pushed it into a model, and it has a temperature, speed, and everything, and it starts predicting whatever output you're looking to do, right? Now, what you do is now you take the model and apply it to a 5 HP engine. It doesn't work. It doesn't work because the training data was only captured for a 2 HP engine. It never had seen a 5 HP engine. So that means it followed closely what the 2 HP engine behavior is. Whereas what we are trying to do is we are trying to apply that particular model to any type of an engine or an engine with any power. So that's overfitting. Underfitting is something wherein the data which you have captured is just too less for a model to capture the underlying pattern of data. So it doesn't work on training, it doesn't work on validation, it will never work in production. That's underfitting, right? The next key concept is our bias and variance, right? So this is as confusing to me as for everyone. When me being in this field for 25 years, I still keep on going back to my textbook definitions, right? So a bias refers to errors from overly simpler assumptions, right? Where variance refers to sensitivity to noise. So in an example, variance is today, if there's a linear relationship between input and output, I say that if the input changes by 1%, the output also changes by 1%, right? Whereas higher the variance, I would say that if my input changes by 1%, my output is changing by 10%. Okay, so that sensitivity to noise is what the variance is. And the key thing for this to work is having a very close balance between bias and variance, right? And including the model complexity. So this chart essentially shows me that how the error, the bias, and the variance play intermingle among each other, and this is where my model needs to sit. Okay, and then last but not the least is the evaluation metric. So we say, oh, I understand the model. Now let me just talk about how do I know that the model is good enough, right? So we capture metrics like accuracy, how accurate the model is, how precise it is, what's the recall, what's the F1 score, and so on and so forth, right? And the last is confusion metrics. It is as confusing to me as for anyone else, but I would want people to look it up, what the confusion metrics in machine learning actually means. And you would be confused as me as well after you go through it. Okay. There was something in the chat session. Is that something which I need to look at? I was not sure. Okay, so let me go to my next slide if we have no questions. So let's talk about the types of machine learning models, right? And there are others, but at a very, very high level, these are the key ML models. With generative AI, things have changed a lot because no one wants to do any one of these, but everyone wants to work on generative AI. But this, in the earlier session, we heard that, okay, the mechanical engineers are still going to stay, right? Because we still, engineering as a discipline, still understand the fundamentals, still understand the logic. Everything else is a program, and I don't need to write a program anymore, right? But if I understand the fundamentals, I understand the logic, I could come up with something which has my name and learning in it. And that's what the key is, right? So let's talk about the types of machine learning. So first is the supervised machine learning. So we say that when I say supervised machine learning, it means that I know what the output would be. Right. So if I say, if my motor runs for an hour, the temperature is going to be whatever, 190 degrees, right? So I know what the output is going to be, right? So we say that in supervised learning, we use label data to learn mapping between the input and the output, right? That this is something typically is an established process, and now I'm trying to predict something, right? So it is, so therefore, a number of algorithms do exist for supervised learning, right? Next is unsupervised learning. So now what we are saying is, okay, here is a process. I don't know what it looks like. I don't know what the output would be, right? So the outputs are unknown, right? So, but I still need to mimic that system. So what do? I use something called as unsupervised learning, right? Wherein I don't have data labels, right? I don't know what the output would be, but the first step, as what every human being learns, is classification, like clustering, right? So standard algorithms, and I try to keep it as close to as English as possible because that's how I understand it as well, right? So simple mechanism of distinguishing between different outputs. That's always a starting point, right? So typically is used for exploratory analytics and early fault detection and so on and so forth. So that's what we call as unsupervised learning, where I don't know what the output look like, right? Reinforcement learning is the next generation of it. When we talk about We talk about agents, right? We talk about robotics, and earlier in the earlier session, we went through an extensive example as to how to train those robots, and robot arms, and all of it, right? So now it's called reinforcement learning, wherein me as an agent, I'm going to learn from the environment, and I'm going to take an action, right? Based on that action, someone is going to tell me whether that action was good or bad, right? If the action is bad, that means I get a penalty, right? And the penalty could be represented by a policy. If an action was good, I get an award, right? So me as an agent now gets started training in terms of maximizing the good side of it, maximizing the award of it, right? So receiving award is the key thing, right? So which is how essentially humans learn, right? So that's the next what we call about reinforcement learning, and we'll go deeper into it, right? Now, if you try and understand and visualize this, there is a method to this madness, right? And typically we start with unsupervised learning. Okay, I don't know what I am going to see from this process. So let me try and classify what the outputs are, right? So I get an initial intuition that, okay, oh, these are green crosses, or these are red crosses and everything. So now I know that I have created a label for this, right? It's a green cross. It's a red cross. It's a label for it, for the input data. Then I say, okay, now I am able to classify it. Now let me start predicting what would come next. Whereas when I get supervised learning, right? So when you say that, oh, okay, now that I have the labels, the next thing comes, green cross comes, I'm going to put it into this box, right? So that's what supervised learning is. The next becomes reinforcement learning. Now what you're saying is, oh, this is all, if you look at this unsupervised, these are textbook, like this is code, right? But this has not been embedded into anything, right? It's not been deployed. It's not in an environment where this model should operate. There's where reinforcement learning comes in, right? So which now uses the classification of unsupervised learning, the prediction of supervised learning, and the policy changes or actions or the whole award penalty mechanism of reinforcement learning to actually bring that model to life. So that's how you start thinking how different types of machine learnings operate in a physical environment. Okay, let me move on, right? And let's now start talking about, let's go a little bit deeper into each of these three learning algorithms, right? So supervised learning first, right? So what supervised learning uses labeled examples to learn a function, this is a mathematical function, right? Which maps the inputs to the output, right? It's typically used for prediction, and sometimes it's used for classification as well, right? So when I say classification, okay, it's something wherein and I need to find out. I should have got a better diagram for this, but let me go through it, right? So what you have is, okay, examples. Oh, animals, right? So I have label data, and right, like all animals, and I have labels. So what does a cow look like? Right, so that's how to go, like, right? And then what I do is I split this label data into training data into what my training data set and validation data set and everything, right? And I pass it through the algorithm, right? And it creates an output, right? Now I compare that output to the label. So if the data about an elephant goes through this model and the output is elephant, all good, right? Because now it has understood, it's starting predicting what an elephant looks like, right? And I run through it multiple times until a state wherein is when I push this data through it, it starts identifying or classifying these data attributes among different types of animals. Now, animals, because it helps make sense, but you could apply it across the board in any process you are trying to classify. Right. The next example is around regression. So regression, there are multiple types of regression. I will talk about it. Is regression essentially predicts whether continuous values, or I think it could do probabilistic values as well. right? And where it is being used is for forecasting, for predictive maintenance, and so on and so forth, right? So key things, classification as well as regression. These do just two high-level examples in terms of how a supervised learning algorithm or model operates, or what the output would be. Okay. So let me go into the algorithms, right? And this takes a little bit deeper, and I just picked up a few algorithms which would be helpful as you start thinking of projects, use cases, problem statements, and so on and so forth, right? So first is linear regression. So linear regression essentially, mathematically, it is y is equal to ax plus b, right? Where x is your input, y is your output, your a is the slope of this, and the c is an error factor, right? So what it does, it establishes a linear relationship between input and output. It's a simple mathematical equation. You'll be able to predict, or you'll be able to use it. Okay. The next is logistic regression, right? So this essentially creates a binary outcome of an input, right? So if I say an example, going back to the animals example, is okay, if I publish data about an elephant into the model, right, and let's say the model does logistic regression, it will tell me whether it's an elephant or whether it's not. Yes or no. That's what logistic regression does. Okay, so typically in terms of anomaly detection or defect detection, right? The first step is whether to define whether it's an anomaly or not, whether it's defect or not, right? Yes or no. That's where the logistic regression comes into play. Right? And mathematically, it's just represented by an S curve. Right? Decision trees, right? Decision trees are something, and I forgot. Where do we, I don't know, if people remember linked list from their first and second engineering, M1, M2, wait, it was M3, I think, a difficult subject, but there's where we use linked list and everything. And there's where we use like type of a decision tree. So when you say decision tree, and let's take an example of 3 or 4 different parameters, right? So pressure, temperature, and let's say speed, right? And you have a data set which has these 3 attributes for whatever 100 different observations. And you need to now start finding out the relationship among these 3, right? So we start with temperature, and you say that, I split the data of temperature between 2, for example, right? And then we say, if the temperature is between 0 and 50, or the temperature is between 51 and 100, that becomes my first decision, right? So for example, here, let's take this example, right? So I start with here, right? Now I am here, right? So temperature is between 0 and 50. Now let me look at pressure, right? And if now we say between 0 and 50 for those data points, the pressure is between 100 and 200 psi and 200 and 300 psi. So I go deeper, right? And then let's say that at a pressure between 100 200 psi, the speed was whatever 5,000 rpm or 7,000 rpm. Now, what I have done is essentially I have taken that data and applied it on a tree-like structure, right? So next time what would happen is I see the data and I see, the temperature is 60 degrees, right? So I'm going to say, okay, the temperature is 60 degrees. What I'm doing is I'm traversing the tree. I'll directly come in here. And then let's say that my pressure is 250 psi. So I come in here. Then once I'm here, now I know the speed could be whatever 7,000 RPM, because that's what the data did show me. What's the earlier data, and now the new data which I'm looking through, which I'm traversing the tree, is brand new, right? But since I'm traversing, I'm going from the top to the bottom, I am essentially eliminating the speeds which are irrelevant. For example, if the temperature is going to be at 45 degrees, right, the speed is never going to be 7,000 RPM. So therefore, I am traversing the correct path of tree, and this gives me the prediction saying if the temperature was this, if the pressure was this, the speed would have been this. And so this is how the decision tree works, right? Random forest is an extension of the decision tree, right? So what it does is, I started with temperature here, right? What random forest does is it starts with temperature, it starts with pressure, it starts with speed. It does randomly, it will generate all these trees, right? And then at the end of the day, based on whether you average out these tree values, right? So average out these nodes wherever they are, or you take the maximum whichever way, right? So that's what the random forest algorithm does. Right? So now if you're seeing, oh, this is simple linear relationship, right? This is a logics relationship, gives me yes or no. Decision tree is something is figuring it out, large amount of data, but this is much more computationally efficient because we could build trees like very, very easily. Okay, so these are the basic algorithms for supervised learning. Okay, now let's go a little bit deeper, and I need to check what time it is. Okay, I have one more hour, 45 minutes. Okay, now we talked about the basic algorithms, right? Now let's talk about a little bit deeper advanced algorithms. So the first one is gradient boosting, right? Now, the earlier in the random forest, what you did, I created hundreds and thousands of different trees and passed data through it, and I essentially built those trees, and then I merged them together, right? As opposed to that, what you do is you built one tree, right? And there is going to be an error, and folks in machine learning would understand more about what the error, what when I say error, what it actually means. For everyone, it's simple: is my output I was expecting 5, right? That's what my prediction was, but the actual was 3. So 5 minus 3 is 2. That's my error, right? And what I need to do is to help my prediction to be as close as possible to the actual, I need to reduce that 2 to 0. So that 5 is predicting and 5 is the output. As simple as that, right? So in gradient boosting, what do we do is whatever residuals which we get, which is that error residuals, I pass it to the next tree. Okay? So I adjust the tree, these nodes and these edges accordingly so that I am passing that error forward, right? What it means is when the next tree gets built, right, it will address that error and reduce that error further, and so on and so forth. So until you get to the last wherein you have the most based minimum error, or your model metrics are the best what you could achieve given the time, the data, and the expense which you would have. When I say expense, it takes money to run these models, right? For a problem which you're trying to solve, right? So that's how you do gradient boosting. A large number of Python packages are available for you to simulate this. I just wanted to make sure you understand what actually it means, right? The next model is support vector mesh machines. We traditionally, we don't use it that much, right? But it has been there for quite some. This was one of the oldest machine learning algorithms around, right? So earlier, what we saw in linear regression, we saw that, okay, the input and output, a single straight line is what we actually did draw, right? And that gave me that equation. But when you're talking about multidimensional data sets, when I say multidimensional, it could be hundreds of dimensions, right? It becomes very, very easy. Sorry, why did I say easy? It becomes very, very difficult to distinguish between these data sets when I'm trying to apply some form of clustering algorithms on it, right? So what SVM introduces is something called as hyperplanes, right? So these are hyperplanes who operate in multi-dimensional ecosystem, right? So what this does is this distributes or clusters these data assets, these input data attributes accordingly. Right? So therefore it understands the nonlinear relationship between these different data attributes. Right? Next is the neural networks, and many people would have been started using neural networks because it is it's the state of art, especially in image recognition, pattern recognition. It's now being all used for time series and so on and so forth. And then the next one is a sensor fusion, which I'll talk about it a bit later. Right? Wherein what you have is you have a series of inputs and you have a series of outputs. And what you have is a hidden layer, which actually where the computation actually happens. So you push in your data inputs, your features, right? And through forward propagation, you process it, and each of these nodes operate on the data, all the input data, and you come up with a prediction what the output is, right? Now that prediction, you compare it what the true value is, right? So when I say, okay, oh, my prediction was 5, but my actual true value is 3, right? That I apply to a loss function. So now what I have to do is my error output is effectively 2 is my error, right? So that error now gets distributed across all of these nodes through backward propagation by the means of weight updates, right? So example, if x2 and z and zf is what I'm getting, right? And the weight in here, the function is here, oh, multiply by 1.1 is for the input data, right? Now we say that, oh, my output is 2, that means it's positive 2. So what do I do? My backward propagation would now say, oh, let me try and multiply it by 0.9, right? So that would reduce the difference between the output and the predicted output. So that way the backward propagation works. So there's quite a bit of literature around the basics of all of this, but this should give you a good starting point in terms of understanding how for what the forward propagation means and what the backward propagation means in neural networks. Okay. And now let me quickly, how much time do I have? I'm sorry. I'm not able to figure out.
So, 9:30.
No, tell me number of minutes. Do I have still 40 more minutes?
Yeah, sir.
Okay, then that's good. Okay, so people would be more aware of these examples, right? And then me, like for example, and I took generally, like, mechanical engineering is a huge field in itself, but I just took a few examples. So let's say, okay, I said mechanical engineering in general, some of it, whether it's in production and aeronautics. So those are something which are close to me. I've done some work in it, so therefore I picked them up, right? And you'll see the same examples repeat across the board, right? So, in the first example is, okay, vibration and temperature data can be used to predict bearing failures, right? So simple methodology to be used by using standard inputs and outputs, right? So historically, you would know, right? You would be keep on measuring the vibration and the and temperature for bearings, right? And then you would know when they actually did fail as well. So you have the huge amount of historical data. Now all you need to do is push that into a regression model to identify the amount of vibration and temperature, which if the bearing says it will fail, So as simple as that. The same thing goes for in production lines, right? So you say the image-based models, so CNNs, which will be able to classify defective parts on your production production line, right? Aeronautics, the same thing. We say engine monitoring for aircraft engine, right, to detect anomalies, and you just multi-sensor data across weather, traffic, all the historical data. One of the interesting things which while I was preparing all of this, I did see that, okay, I could predict flight delays as well using this data. That was an interesting learning for me as well. And right, so these are the examples of supervised learning, because here we have all the input data which we need. We know what the output would look like because of all the historical data which we have collected. And these algorithms would be able to help us to predict the next output based on the input data we captured going forward. Okay, next, let me see. Next. Okay, now let's talk about unsupervised learning. Right. So what does unsupervised learning do? Unsupervised learning learns patterns from unlabeled data. Right. So it's a method of clustering things together, bringing things together. Right. In the earlier lecture, there was an example, right, wherein I tell a child that go and fetch an apple. Right. I don't have, and I teach the person, the child to go and fetch an apple. The next time I say, okay, go and fetch a book. Right. Now, it's a similar method, it's a similar action, right? What the child has to learn is the way he or she did go and fetch the apple, the same way he or she has to go and fetch the book as well. So essentially, I have clubbed them together, those two actions, and they say they are the same. I just have to follow the same instructions. I don't have to go somewhere out and get the book, right? The book is just lying there. So that's how you think when I talk about clustering. Okay, so what we say is, oh, clustering groups similar data points, helping identifying operating mode or defect types. Like in the mechanical industry, we talk about defects. So clustering the type of defects together so that I know the root cause of a cluster of defects is A, and to address those defects, I just need to fix that root cause A, and therefore those defects would go away. So identifying which of those defects I should address, or clustering is a very good example to do it, right? So again, so when we say why does it even matter? So, most of the engineering data is unlabeled, right? And it is unlabeled or is huge amount of data. I don't know what it actually means, whether it was a defect, whether it was a failure, or there was some other problem. I really don't know, because I get millions of data points every second from every sensor. There's no way I'm going to start tagging, okay, this is a defect, this is not a defect, and so on and so forth. So I need some intuition in collecting these outputs together so that I could address them statistically and not individually. Okay, so unsupervised learning mimics closely to what we do in stars. Okay, so therefore, so we say that, okay, oh, it will help engineers understand system behavior and detect unusual patterns. That's what statistics does, right? It generalizes data up to a certain point wherein defects or anomalies start popping up, and that's what I try and address. Okay, so that's what unsupervised learning actually, that's how it works, right? Now, what are some of the algorithms, right? So, and these are only a few. There are a large number of example. K-means also has a large number of different variations of algorithms, right? So, I mean, if I just talk about K-means, say that what it does is it takes all the unlabeled data, right? And let's say these are temperature readings of a motor or of an engine, right? And what I have to do is I say that I need to apply a k-means algorithm on top of it, right? So we say that, okay, let me cluster. When I say group, when I say cluster, club these data attributes into closely related groupings, right? So we say, oh, labeled clusters we call, and K is a number of clusters. Okay, and then we say that when I say what's the mean, so what I do is I cluster them together, club them together, and I find a mean. And what I try to do is I create this cluster as it's a green X. Let's say it's a green X, right? So the next new data attribute which would come, mathematically, what am I doing is, oh, let's say that the input is 100, right? And then I have this cluster with a mean of 80, right? So it says that, okay, all the temperature attributes, temperature around 80 plus minus whatever the circle tells me, and circle, because it's easy to understand, it could be three-dimensional, right? We say that, okay, everything around here, around 80 should be part of this. So like it comes to 100, it will be part of this cluster. If it comes 500, it will be part of this cluster. So in that way, you visualize, think that, okay, when new data comes in, where am I putting this? I'm choosing, I'm sorting, essentially, how the child sorts different objects, right? That's what I'm trying to do with different measures of closeness. Here I use means, there could be other mathematical functions you could apply. How do I use this? Simple example, right, is temperature. We talked about temperature, but we know that for certain temperatures, the engine would fail, right? So I get unlabeled. I don't know where it's going to fit, right? And then I push in the data. It doesn't fit in any of these clusters because this is standard operating temperature ranges, right? If it doesn't fit in, the moment I see that unlabeled, that data, which is 1000 degrees, I know that this engine is going to fail. So I use this algorithm to identify anomalies in that way, right? Establish standard clusters, right? Make sure that all the new inputs which come in fall in any of these clusters. If it doesn't fall in any of these clusters, there's a problem. As simple as that, right? Say on similar lines, hierarchical clustering. Talked about trees earlier. On similar lines, you do the same thing, right? So you create tree-like structures. The way, it's just a different representation. Here you are saying, okay, I am collecting those data attributes around the mean of those data attributes, right? Here I'm just creating trees. It's just a different representation of it is, right? And typically, as K means, like the way I would start is I would start with hierarchical clustering to identify how many hierarchies I could create. Using those hierarchies, I've determined what K would be, and therefore I would define all those clusters in there. So it becomes easy for computation. A DB scan is, again, to be frank, I don't understand DB scan very well because I never worked in it, but I just added it in here just to make sure that, okay, I make it a complete story. Right, I'm sorry, I don't really understand, but you are more than welcome to go into details. There are large number of articles around in Medium and other channels wherein you could understand what DB scan does. Okay, let me go to a few advanced algorithms in unsupervised learning as well. Right, so one what we call is a principal component analysis. Right, and the second is autoencoder. Then I will go into deep. PCA is I wouldn't say it's an algorithm, but it's a methodology to identify relationship among large number of attributes. Right. So let's say that I'm going to capture, or I'm reading data from a large number of sensors on an aircraft engine, right? It's going to capture, it's going to capture temperature, pressure, speed, wind speed, what else could it capture? It could capture cloud coverage and so on and so forth, right? Because it's just flying, or height from like how high it is flying and everything, right? Large number of attributes which you have, right? And now you are saying that what I'm trying to predict is I'm trying to predict engine failure. That's the problem which I have, right? But because there are large number of attributes, and they could be hundreds and thousands of those different, and when I say attributes, it's an individual data point which is independent of each other, right? Now, modeling this mathematically, even through a machine learning on a large neural networks, becomes very, very difficult. When I say difficult, that means the model never gets trained. That means its output never matches the predicted output never matches the actual output. So what do? We apply a methodology called principal component analysis, right? Which helps me identify the relationship between all of these attributes, right? It helps me identify let's say if I have 100 different attributes, essentially 100 different type of sensors which are pushing data to me, I would identify the top 10 sensors which actually make a difference to the output. Right? So if I change if the sensor output of a sensor 1 changes, the output of the actual model changes. For some of the sensor outputs, it doesn't make any difference for me. Right? So what I do is principal component analysis allows me to identify the top N, and you could define what N are the top N inputs or components which would go into the model. Right? And because it's multidimensional in nature, it becomes very, very difficult to even visualize. We find difficult visualizing 3-dimensional models, but this is a model which has 100 different dimensions. Right? Or the data landscape has 100 different dimensions. Okay? So PCA allows us to transform it into a layout which I could then easily apply to a model. Right? One way is essentially I'm simplifying it. Right? I'm reducing noise, so to speak, because I'm eliminating the sensor outputs. I'm not going to use sensor outputs which don't affect the outcome of that particular model or that particular process. Right? So therefore, PCA is used for visualization because it helps me understand the relationship between the attributes, and also helps me eliminate noise, which eliminate the data attributes which are irrelevant for the model to talk. Right? Next, so this is the methodology, and the autoencoders is a way to actually implement it. Right? And there are a large number of autoencoders, from variation autoencoders to denoising autoencoders to sparse autoencoders. Right? And I have added a few details which should get you started in this. But when we talk about neural networks, those are the key things that all of these autoencoders are again also used in large language models as well, to eliminate irrelevant questions which you ask GPT, and eliminate irrelevant strings in it, so that I could actually get the question which the user is asking. That's another use of an autoencoder. Right? Let me see. Let me move on. Examples like for unsupervised, we talk about clustering. Like in this example, I think everyone should be able to relate to it. The operating modes of the machines, it's idle, load, or overload. And you could use any attribute. This essentially, if the engine is not running, the RPM is 0, it's idle, right? And however you interpret it, right? And then if it goes beyond any one of these, or if it goes into if the input data says that it is part of this overload cluster, that means it's a problem, right? And you could use multiple attributes, whether it's vibrations and temperature, speed, and so on and so forth, right? In production, as I said earlier, you could identify different defect types based on images on your production line, right? In aeronautics, the same example, like flight trajectories, you could identify a cluster of flight trajectories. And this could be unusual engine behavior, it could be pilot behavior, it could be weather behavior as well. And based on that, my different attributes changes, and that particular flight gets clustered into a particular aspect of what I am trying to solve for. Right? So those just examples of unsupervised learning. Next is the reinforcement learning. So this is the talk of the day, because all our large language models, the basics is reinforcement learning, right? So what is the reinforced learning is all about? Reinforcement learning, it trains an agent, right, to make decisions by interacting with an environment. Right? The agent receives rewards or penalties based on action. And over time, it generates a policy, it creates a policy that maximizes cumulative reward. Right? So now let me see how I could explain this intuitively, right? So the earlier example, right? When we ask a child to go and fetch a book or an apple, if the child fetches the apple, okay, we reinforce that action saying good job. As simple as that. The child understands it, creates a policy. If I listen to an adult, right, I get appreciated. So next time you tell something, the more and more you provide directions and the child follows, that policy gets ingrained into the child's brain or that machine learning model, right? In case the child doesn't follow the action, what do? We either scold the child, or nowadays we don't hit anyone, but scold the child, we just express that it's not good, right? The child remembers that becomes a penalty for the child, saying, I shouldn't be doing this, right? And in that way, the child learns from the environment which he or she is operating in. What is good, what's bad, right? That creates those policy or it essentially hardens those neurons in the brain so that the next time someone says, they know this is what they had to do because that's what the good looks like, right? That's the simplest explanation of what reinforcement learning does, right? And what the variations in it wherein, okay, you could take a model, you could put it into a different environment and it could start learning from that point in time and so on and so forth. But for now, this should be good enough, right? So in here, the key components, what the agent does in this case is observes the state of the environment and chooses the action, right? And then environment responds with a new state and a reward signal. And this feedback loops drives learning. Another example is autonomous cars. That's what the likes of Teslas and BYDs and others do. It's just that their action typically is the same, right? But their reading of the environment is different. Like Tesla uses cameras, others uses LiDAR and so on and so forth, right? But it's the same. It's reading and inputs from the environment, right? If it is going to drive the car on the straight road, all good. If it's going to stop at the red light, the environment says it's good, and then it learns saying, okay, I need to stop at the red light, or I shouldn't hit a pedestrian, and so on and so forth. That's how reinforcement learning would work. And it does continuous learning of this, right? So what we say in here, why is it so powerful? It can learn optimal control, right? So I could always write a program to drive an autonomous car, saying that, okay, I should stop at the red light. I should stop when I see a pedestrian at the crossing, right? I should go when there's a green light. Yeah, simple set of instructions, and the car would follow, right? But that's deterministic set of policies, but real life, it's different, right? Suddenly, let's say there's a traffic stop, right? And everything is a red light or everything is green, whatever reason, there's an accident, something like that. I cannot code for it. That is something which the model has to learn by experiencing it. That's what Tesla does, right? Okay, well, why do their cars drive millions and millions of miles? Because they are learning at the same time. They are experiencing each and every possible scenario they could get into, and at the same time, try and generalize it for something which they have not seen as well, or very close to it. So therefore, reinforcement learning is more and more powerful. Okay. Next, so what are the different types of reinforcement learning, right? Q learning. So essentially, what Q learning is implementation of the earlier one, right? So what you have is you have a state and an action, saying that okay, so let's say that the RPM is 5,000 RPM and the temperature is 200 degrees, right? Now, if I were to say that, oh, let me increase the RPM as an action, right? Like to 10,000 RPM, right? And I'm going to read the state. The state is going to be whatever 1,000 degrees Celsius. Now, that state and action and the value that engine is going to blow, right? So now what I say that no, the action was wrong, right? You cannot make it to 10,000 RPM. You need to come down low, right? So now what's happening is now based on the actions which I'm going to take and the state of the environment I'm reading, I'm taking whatever input comes in, I'm just reading and I'm creating this table. Essentially, this is what it actually does. It creates a table based on a state and action and the value, what good looks like. Right. Deep queue networks on similar lines, but it runs at a higher dimensional environment. So here we had only, okay, I am just manipulating 2 or 3 different attributes, right? Here I do a multi-dimensional environment, like whether it's games or robotics or cars and so on and so forth. I use deep queue networks, right? What I'm trying to do is the difference between policy gradient methods and deep queue networks is in DQNs, I am changing the action which that agent is taking. Right? Accordingly, I am going to change the policy. Right? In the policy gradient method, you turn it around. What you do is you keep on updating the policy. The action takes automatically. But I don't have to take an action. So it's something as similar as a thermostat, right? A thermostat, all I need to do is I need to set a temperature range. After that, based on what the output is, it takes an action, right? But a policy could be something that, okay, in summer, the temperature range should be whatever A to B. In winter, it should be between X to Y, right? But based on the changes in the temperature, the changes in the weather, the temperature in the seasons and everything, all I could do is I could update the policy, right? And let the action and the state and the environment operate accordingly. So it's just the other way of doing the same thing. Right? So deep queue networks and policy, why is it police? Okay, spelling mistakes. I should remember that. Policy gradient methods essentially are 2 sides of the same coin, right? I'm just tweaking something different, but the output action is still the same. Okay, so let's talk about reinforcement learning examples. This you did go to earlier session, right? Like robotic arm trajectories for speed and precision. So, right, in production, you could optimize the process parameters, right? So scheduling, routing, you could do many things, right? Aeronautics, UAVs, you could navigate them automatically in dynamic environments. So, when I say dynamic environments, so it could be wind speed, it could be temperature, it could be height, and so on and so forth, right? Like, okay, optimize flight control for what am I looking to do? I'm trying to optimize for fuel efficiency and stability. So that's where within you use reinforcement learning, because I don't know what I'm going to get. I need to learn from the environment, right? So what are some of the top ML models? So we talked about large number of models, and I know I quickly ran through many of them, but I'm just hoping to get you acquainted at a very high level what it means, so that then it will get you started to go deeper into each of them, right? But within the industries, traditionally, what are the top models which we use? Random forest is obviously the first one we talk about. XGBoost is majority of the ML models which I see across the industry. Like for me, coming from financial services, or I work with people in energy, I work with people, now I'll work with you all as well, right? So there I see XGBoost is one of the most strongest model which people use. Reason being, it's cheap, it works, it fits the problem. As simple as that, right? CNNs then obviously for image-based models, to whether it be pattern recognition, whether it be it in your autonomous vehicles or your UAVs, like large, and then the next thing around generative models, right, which generates images and whatnot. So we use the CNNs in a number of those areas. In LSTMs, these typically are used for time series models, right? So long short-term memory, because it essentially maximizes the good in the model over a long period of time. So that's what LSTM means. Transformers are use attention mechanisms. So these are inputs which goes to the model which try and tweak their output, right? Transformers are the core for your large language models today, and everything has been built on top of it. So these are top ML models which I have come across, and I have seen it used across the industry. Right. Again, now what I'm going to talk about is some examples. Should be similar to what we had talked about earlier, right? But some examples in predictive maintenance. And so these are something examples which we could do projects on, right? And a large amount of research literature is around, we just need to implement or make them happen, right? So with predictive improvements, digital twins, like fault diagnosis is something which we could work on in mechanical engineering applications. Same thing for production. These are for production lines, right? So quality inspections, we could use CNNs to detect defects with high accuracy. So when we talk about a large scale production pipeline, and let's say the simplest one, okay, it's something which creates nuts as the simplest example, right? It'll create thousands of different nuts through the production line, where it becomes very, very difficult for a human to identify and detect defects. So CNNs typically are used in those production lines to not only capture each and every of that nut, compare it with what a good nut looks like. And I'm using very, very simple language. That's how I understand everything is, and then figure out whether this meets my criteria or not, right? And then based on that, I would push it out or make changes to my process to make sure that if any errors are there, they're within the margin. Yeah, same thing for process optimization, right? For supply chain forecasting, for demand prediction, inventory needs. This is something which I'm currently working on anyway, on supply chain forecasting, just as an FYI. For aeronautics, the same thing. For engine health monitoring, for autonomous flights, for structural health monitoring. Many of these models would be used. And I'm not saying, for example, for structural health monitoring, I'm going to use a model, right? No, that won't work, because that model solves a very small part of it, right? It helps, some of it will be help me identify what does a crack mean, right? Or at what point in time I need to address that crack in a machine, right? So that's one. Identification is one, wherein I use clustering. The next thing is I use regression to predict it, right? Third is, okay, I need to put it into life, wherein in using an RL model, I will not only started predicting, but also taking actions around what needs to be done. Whether I need to send a notification to the engineer saying, here's a potential problem I see, and we need to address something like that, right? So it's a combination of all those models, what we did go through today, we should address these applications. Okay. So what's next? What is the next thing which is coming up in these models, right? So for supervised learning, we are obviously doing like data efficient training, right? So, and a very good example in my world is this, right? So let's say that I am trying to predict the life expectancy of whatever, 3.5 billion people we have on this earth. Yes, right? But I cannot capture all the data, right? So what do I need to do is, and I need to do it much, much more quicker. So I use something called as synthetic data generation. I have some data, the rest I created, right? So that's how do I efficiently train models which are data intensive, right? At the same time, there is a cost for data collection. So for example, all the large language models, we have GPT-5 or whatever, Grok and others, they have been trained on all the publicly available data on the internet, which is huge. Therefore, it costs so much to build foundational models, right? So more and more research has been being done is how do I address that cost and efficiently train the model without consuming all the data which is available in the world, right? So that's the first one, right? The next one is around adversarial training, right? So there's new work which has been done on this. So this is an extension of what an RL model does. When we would have heard about GAN networks and others, which talks about generative adversarial models. So that's an area which is being researched on, right? Foundational models, right? Saying that today we have huge amount of data across the board, right? From either it's from fluid dynamics, material science, and so on and so forth. Now, this data is sitting in different universities, different industries, and all of it, right? But what we need is we need to create a foundational model for fluid dynamics. That means I need to pull all the data available across the board, bring it together, right? Build a model like a large language model for fluid dynamics. I'm not saying it's going to predict language, but it's going to do something else, right? But create a foundational model for fluid dynamics. Then every industry, every researcher, every university is going to use that fluid dynamics foundational model to do the next thing within whatever narrow domain they are operating in, right? So these new foundational models are currently being built. The next is multimodal supervised learning. So we talked about the robotics example earlier, right? Is something which you could do that across different sensors, images, and so on and so forth, right? So that's how. So there's where supervised learning is going today, right? Unsupervised learning, right? So something similar, like obviously generative models are the key in here, right? But the new thing which is called physics-aware unsupervised models. So this is something which was touched upon in the earlier session, wherein you apply the laws of physics on your model, right? Which becomes constraints. Otherwise, what's going to happen is I could push any data into it, it'll learn what the data has to say, and it would come up with outputs which are physically impossible. Right? Oh, I could say that it could start predicting that the temperature of this engine is going to be 0 degrees Fahrenheit. It's not going to happen, right? But it did it because there was some issue with the data, something happened, someone screwed up, and therefore that's how it's predicting, right? And we have a big problem. So constraints like that, when applied on the model, will make sure that my model operates within the boundaries and constraints of physics, maths, and science. So that's what's happening now. Right? Newer algorithms are being built for clustering and manifold learning. Right, these are again high dimensional sensor data. What we talked about was very, very basic, but there are different ways of representing high dimensional data into different latent spaces. So that's what research has been focused on. Self-supervised learning is the same thing, but it's a combination of everything which we talked about. That's what it does, right? Reinforcement learning. So this is the last type of machine learning model, right? So the two things, right, is the key things, and I'll talk about only of these two, because foundational models are there and they are going to continue to evolve and on all of it, right? Offline and batch RL. So today we talked about reinforcement learning models, and we sort of talk about autonomous cars, right? So there's a big problem wherein I put a car on the road and the model has not learned anything, right? So I start with the blank model and then I start the car. And now it is reading the environment and it is driving, right? But it is going to face n number of problems. It's going to create accidents, so on and so forth. So I cannot train the model in real life. So what do I need to do? I need to train the model offline. So what do? Is I take a traditional car, I do read everything, and human is driving. I read everything around environment, all the actions with the human taking. That creates a huge data set for me to train. Then I take the data and I train the autonomous car, the model which sits in it. Once it is trained, then I plug in that model into the car and then let it go. So it has learned how to drive based on historical data without online exploration. But this has a problem, right? Where is the problem? So Mars Land Rover, the Mars rover, right? I don't know what the environment is going to look like, right? I don't have any historical data how that rover should operate, right? So where does that get us? Oh, it gets us to the foundational models, right? Wherein what do I do is I create a foundational model to simulate the environment. Within that environment, which keeps on actioning, because I cannot go to Mars to train the model, right? So that the foundation model simulates the environment, the RL model operates in that environment, and they both learn together. So that's the next thing, right? And obviously multi-agent RL, so swarm robotics, supply chain optimization, distribute control is huge amount of data which goes back and forth among large number of entities in supply chain or even in small swarm robotics, right? Wherein you have a large number of those small aircraft, right? And they create huge displays and everything. They are talking to each other, right? So in that case, how does that model operate is where the multi-agent RL would work when different agents talk to each other. And if people have come across this within the Gen AI world around agentic frameworks or agent-to-agent communication or model context protocol frameworks and everything, there where you see there are multiple agents which are talking to each other and taking actions or a set of actions to make everything happen. So that's what a multi-agent RL would do. Okay. I just created some examples, case studies, just to start getting people thinking when you are trying to address a problem. How do you go about applying what you learn today or what you learn for all the next, whatever, 50, 60 years, and apply your ML approach in solving that problem, right? So, and let me see. Okay, I think I have run out of time. But let me go through this one and then we could open up for questions, right? So we say that one of the example is as an airline, like Delta or Air India, I need to identify abnormal flight trajectories. So typically when someone flies from Mumbai to London, there is a flight path which they have to follow, right? But for a number of reasons, the pilot could deviate from the flight. So now I have large amount of data, right? And to identify whether that's a true deviation or why the deviation was, right? And that could indicate whether the pilot was not behaving or there were weather or there were sensors, because for foreign aircraft, right? So what type of data am I actually going to capture to do all of this, right? So I say I have multivariate telemetry. That means altitude, large number of attributes or data values on altitude, speed, pitch, roll. So I get all of this, right? Sampling rate at 1 hertz. I don't know how to interpret that, right? But there are no anomalies, right? Because I don't know what's wrong in here. So it's an unsupervised problem. I don't know how to define. So what do I do is apply an ML approach. So the ML approach which I do is unsupervised learning. So essentially a clustering algorithm, right? And it's a multi-class clustering algorithm, right? So I want to cluster normal flight patterns and detect deviations. What's the output, right? So typically, what does the model architecture look like, right? So first I use autoencoders. So this essentially eliminates the noise in the data, right? So I do that, right? Then the output of it I get, I create like the input which goes into is a telemetry vector. So all these attributes I create at 20 dimensions. So there are 20 different attributes, right? And then the error output which gets from what the actual deviation look like and what I'm getting is what the reconstruction error is. And I could use dbScan for the cluster formation. So with this approach, this architecture, I'll be able to identify anomalies. So some of the results which you could like, oh, it was able to correctly group 95% of known anomalies in all historical data, right? It also created clusters for crosswind events. So now this is something where in a flight is going a strong straight line or everything is all good, but if there's a crosswind, it will move, it will shift from the flight path. No fault of anyone else, right? The pilot is going, the engine speed and all of it is all good, right? But there was crosswind. So that was clubbed together, saying that this flight deviation was because of crosswinds, right? And so that's what it does. So what kind of engineering considerations we would want to have? So it required synchronization of all telemetry channels. So all the data I should get at one point, every 1 hertz or every second I need to get the data, right? There's no point in getting data for altitude after every 10 minutes and speed every 1 second. No, so it needs to be synchronized, right? The latent space drift monitored monthly. This is because things would change, flight paths would change, weather would change. So I need to make sure that as the data drifts, right, my model also accordingly drifts. And then it's effectively is integrated in the flight operations dashboard so that people could actually understand what's happening, what's the root cause of a flight trajectory deviation, right? If there is any action which is required to address it. So that's just one case study, and then there are let me see, this for additive manufacturing, for multi-fusion fusion. This is what we talked about earlier, right? Using LiDAR, camera, and radar encoder, and then bringing all of these outputs together, right, to identify objects on the road. Okay. So I'll share the screen. I'll share the deck, and then let me know if you have any questions. I know I have run out of time.
Thank you, sir. Participant can ask question. Yes. Participant can unmute.
Yes, sir. So thank you so much for your valuable presentation, sir. Then more informative, and almost you have covered about ML, the various application of mechanical engineering. So I have some doubt in this, sir. So
Yeah.
you also explained about supervised machine learning, and unsupervised machine learning, reinforcement learning, and also that there is a semi-supervised learning also it is there, no, sir. So when we can use that semi-supervised learning, sir? So you have
So semi-supervised learning is a combination of unsupervised and supervised learning based on whether you have good amount of data, right? So an example is, okay, or use clustering algorithms to effectively define the labels of your outputs, right? That becomes the first step. Now what you have is you have a labeled data set, then you use that to do supervised learning. So you use that to do regression, whatever model you want to use for regression. So it's a combination of both.
okay, right, sir. So that what is the application, sir, where that semi-supervised learning will
Yeah,
come?
so semi-supervised learning is typically used when you have large amount of unlabeled data. One, right? Or you have sparse labeled data. So if you have unlabeled data and a huge amount of it, you use your clustering algorithms to define the labels, right? And then once you have defined labels, then you say, okay, oh, this group of attributes, whenever they come together, this is what the output should be. and then you use that and put it into your neural network or transformer model. So in that way, so that's the reason I said it's a combination of both, right? The other one is wherein you say that I really don't have large amount of label data and have sparse data, and I only have a few records. So what do? Is I use that data to define my clusters, right? Within those clusters, I create synthetic data. Now then I have that, okay, oh, now I have data across the board, and I have used a part of clustering, right? And then plugged it into, created that data and then put it into my classification algorithm. So in that way, you use it. If you have a problem statement, then I could actually tell you how to do it. Otherwise, it becomes a theoretical conversation.
Okay. Hello, sir. Good evening, sir.
Hi.
This is Dr. Arun Karthikeyan speaking here, sir.
Yeah. Hi. Hello.
Yes, sir. Actually, it was a wonderful session, sir. I think within a short period of time, you have explained about supervised, unsupervised, and reinforced learning. It's a wonderful session, sir. And
Thank you.
visually, it was very beautiful, sir. Thank you so much for the wonderful presentation.
Sure. Thank you. Thank you.
Yes, sir. Yes, sir. Sir, actually, we are from core.
I'm sorry I lost you.
Hello, sir. Hello, sir.
Sir, please ask question, sir. Please.
Yes, sir. Sir, actually, we are from mechanical engineering, sir. We are not aware of all the programming languages. So, whatever you discussed, past 1 hour, supervised, unsupervised learning, theoretically, we have understand the things. But how we can effectively utilize, how the things will be converted into the effectiveness, sir, for our experimentation.
So there are large number of tools which are available in the market. One of them we call as Klein. It's a code generator tool. I forgot where it came from, OpenAI or someone, right? Wherein what you could do is you have a problem statement, right?
Yes, sir. I have problems, sir. For example, I am doing machining. I have a 3 input parameters. I have a
Yes.
3 output parameters. So I nearly 27 experiment I have conducted, sir. So I
Yes.
want to find out the optimum condition as well as
Yes.
So yes, sir.
Okay. So what you need help in actually writing the code to build a model, which then you could start to
Yes, sir.
use for prediction.
We can
That's
apply
what you
this
want to do, right?
Yes, sir.
So
Yes, sir. Yes, sir.
what you need to do is you need to detail out each and every step what you actually did, right? Including all the data attributes which you captured, what the output which you look for, anything, and use a tool like Klein, CLINE, which would help
Okay.
you generate the code which is required to take your input data, right? And okay, we assume that we're going to build a regression model, right? Take your input data, train the model, right? Make sure that the model works correctly, right? And also help you deploy the model. So what a client is going to do is client is going to create all the code base for you. It'll give you instructions how to run it, how to execute it, and all of it, right? But whether it's actually working or not is up to you.
Okay.
You decide, right? So even if you don't have programming, even if you don't have you don't need to know Python, right, to do all of this, right? Because there are tools which would create the Python code for you. But you need to come up with that mindset in terms of the domain knowledge which you have, what makes sense, what doesn't make sense, and is it truly working?
Okay.
With that, you would be able to do it.
But yes, sir. But I have a limited in data, sir, because the experimentation is very costly.
That's fine.
If I conduct,
that's fine. Sir. Yeah, see, that's fine. So that's the first step, right? So if you think that even with 10 records, you can train a model, you can train a model. I'm not saying you cannot train it, right? But at some point in time, when you say that, okay, this looks good, right? But I want to make it better. At that point in time, we touched upon generating synthetic data. So you could use those GAN type of models wherein you could use the input data which you have created, whatever 27 readings which you have, right? And you could
Yes.
create large number of data records or records which would mimic your current system. They are not actual readings, but they are synthetic data. That will allow you to create large amount of data. Then you use the data to train the model.
Okay. So is there any possibility for overfitting, sir, if I create or generate the data? So that there will be a problem now, sir,
There
actually.
would be a problem, right? So, but at the same time, you're generating synthetic data. You need to add noise to it.
Okay.
So you don't want the model to fit 100% on your data, right?
Correct.
So overfitting is a problem when you have all the data in the world and you're pushing it to the model. You're not testing it for anything, right? So even though you say that out of the 27 records you have, you're going to use whatever 15 records to train, right? And 7 records, whatever 12 records to test and everything. So you do the same thing on synthetic data as well. So it will not
Okay.
overfit. It will not underfitting is a problem because you have limited data, but generating synthetic data and using it will not lead to overfitting.
Okay. Okay, sir. I think, yeah. Thank you so much, sir. I got an answer actually. Whatever I'm expected. So I was received that, sir. Thank you so much, sir. So if possibilities, we will see you in some other seminars, sir, with
Sure.
answer.
Yeah. Yeah.
Sir, can you tell me, repeat that software, sir? Client code.
Right.
Cline, CLINE. Like,
Okay.
you see, even GPT could do it for you, right? If you tell, okay, write me a code, skeleton code to train a regression model, it could write it for you. But client does the job a little bit better because you could provide it instructions, step-by-step instructions, and it will do the work for you.
Okay. Any more question?
Okay, sir.
Participant, any more question?
Sir, good evening.
Yeah.
Sir, I have one doubt. For what cases I have to use XG boost, and what will be the efficiency instead of XG boost if I use random forest?
Oh, that's a tricky question. I don't know the answer to it. Hey, see,
because when we are looking into the ML algorithm, there are a lot of algorithms developing day by day.
yeah, there are.
In what scenario XG boost will be very much useful?
So I really don't have an answer top of my mind, right? I may have most likely asked GPT because there's so many things happening, right? So I'm really not sure. But the way I see it is this, right? Is if you have a problem, right? And which can be solved by a linear regression model, which is one of the simplest model, right?
Yeah.
Don't try to use neural networks.
Okay.
Right? So the model should fit the problem and the model should fit what output you're looking for. You could create you could create a large language model which will still solve your linear regression problem. But would you want to do that? No. So always start with the most basic model based on the data which you have, right, and the output which you are looking for. If a particular model doesn't meet the requirements of what you're trying to achieve, the problem you're trying to solve, you move to the next sophisticated version. And I don't
No,
know whether
actually,
XGBoost or Random
Actually,
Forest where
see,
they stand.
my research area is condition modeling. Okay, I deal with most of the time vibration data, which is a very high random in nature,
Right.
and it won't fit in the linear model, which I already tried,
Yes.
and not
Yeah.
even the logistic regression also.
Yeah.
So for classification, so what will be the benefit if I use the XG boost? Can I use in such scenarios where there is a very non-linearity in the data?
Yeah. I don't see an issue.
Okay. Okay. Thank you.
Yes. Okay. I sincerely thank you, our esteemed expert Mr. Ajit Patil, sir. Sir, beautifully
Sure.
explained importance of data and machine learning pipeline, machine learning key concepts, then types of machine learning, advanced algorithm. Also, sir have highlighted the mechanical and aeronautical engineering examples, including supervised, unsupervised, and reinforced learning, and the discussion on top ML model. Sir also highlighted the real-time case studies and the clear direction provided for future research in machine learning across mechanical and emerging application domain, where especially valuable and thankful. So once again, I am very much thankful on behalf of ATAL Faculty Development Program Organizing Committee. Thank you, sir.
Thank you. Thank you. Thank you. Have a nice evening, everyone.
Yes, yes. Thank you, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Sir, shall we leave the meeting, sir, if you don't mind?
Yes, yes, sir.
Oh, okay, sir. Thank you.